Swayam Prabha. Digital India. Educated India.
This is the third lecture on gas turbine cycle analysis. Regarding contents of the lecture are cycle with reheat and heat exchanger. We'll perform also the cycle analysis with intercooled compressors. Then we'll learn to actual gas turbine cycle. We'll consider the compression and turbine efficiency, pressure losses in heat exchanger combustion chamber, then heat exchanger effectiveness. So it will be considered now not perfect. Furthermore, we'll discuss on mechanical losses, variation of specific speed with temperature, changes of mass flows in turbine and compressors. I'll discuss cycle analysis with reheat and heat exchanger. I've already told that efficiency of a reheat cycle is less than that of a simple gas turbine cycle. Thus, the reduction in efficiency of a reheat cycle can be compensated by adding a heat exchanger as shown in the figure. Thus, the schematic of a reheat with heat exchanger cycle has been illustrated in figure 8, where I have considered a reheat cycles, that means a compressor followed by the combustion chamber, then HPT and LPT turbine. The gas is reheated between the HPT and LPT, and then turbine is connected to the compressor, and also it rotates the generator to produce electricity. Further, exhaust from the LPT is passing through now heat exchanger, and therefore it is utilizing the exhaust temperature, which is normally higher than the compressor outlet temperature. So thus, look here, a heat exchanger between the compressor and the LPT is also provided to utilize the energy. So TS diagram of the reheat with a heat exchanger has been illustrated here, where 1, 2, 3, 4, 5, 6, 1, the reheat cycle. In this case, 1, 2 is the isentropic compression in the compressor, and 3, 4 is the isentropic expansion of gases in high pressure turbine HPT. 4, 5 is the constant pressure heat addition in reheater combustor, and 5, 6 isentropic expansion in LPT turbine. The process 2, 7 occurring in the heat exchanger that utilizes the high exhaust temperature of LPT turbine. So the heat is adding in the combustion chamber is represented here by the process T7. Therefore, we have utilized here a considerable energy because of addition of heat exchanger as illustrated before. Thus, we can conclude that the reheat cycle with a heat exchanger increases both efficiency and the specific work output of the cycle. Now I'll discuss on gas turbine cycle with intercooled compressor. What has been done here, that compression process has been divided into two compressor. One is denoted by LP compressor, that's low pressure compressor. Another is HP compressor, high pressure compressor. And in between the two compressor, an intercooler is provided. That means the compressed air being cooled by some heat sink. So what has been done here? Air is sucked by the LP compressor and it is being compressed, and then it's cooled in an intercooler, and then it is again compressed in a high pressure compressors, then pushed to combustion chamber where heat is added, then it is expanded. Now, TS diagram has been illustrated here, where intercooled gas turbine cycle is 1, 2, 3, 4, 5, 6, 1. 1, 2 represents isentropic compression in the LP compressor. 2, 3 is the intercooling has been done at constant pressure. That is, compressed gas again has been cooled to the initial temperature. So now we have assumed T3 should be equal to T1, and then again it's being compressed in a HP compressor and then heated in the combustion chamber at constant pressure. Heat addition is the 4, 5, and then expanded in the turbine to produce work output. And the turbine work output has been divided. One part runs the compressor, another is utilized to generate electricity. Thus, the cooling of air in between two stages of compressor is known as intercooling, and this intercooling reduces the work compression, and thereby it increases the specific work output of the cycle with a decrease in thermal efficiency. So here also, specific work output increases while the thermal efficiency decreases. Further, I like to express that loss in efficiency due to intercooling can be compensated by providing a heat exchanger and thereby utilizing the exhaust heat. Furthermore, for perfect intercooling, we can say T3 is equal to T1. That means after compression, it is being cooled again at the same temperature at constant pressure. Now, the specific work output can be expressed as W is equal to turbine work minus 2 compressor works. So Cp into T5 minus T6 minus Cp into T2 minus T1 minus Cp into T4 minus T3. Furthermore, one can appreciate that Cp into T4 minus T3 is less than Cp into T2 dash minus T2, which is the state point to T2 dash. If from 1, if you would have continued the isentropic compression up to the pressure P4, then we land to the point 2 dash. And we know the constant pressure line in TS diagram are diverging. Therefore, Cp into T4 minus T3 is less than Cp into T2 dash minus T2. Thus, some work has been saved because of intercooling, and thereby the specific work output for intercooled cycle is more than that of the simple gas turbine cycle. Let us consider now the efficiency of the cycle. So the efficiency can be expressed as eta Cp to T5 minus T6 minus Cp into T2 minus T1 minus Cp into T4 minus T3. That means work done, specific work done, divided by the heat added Cp into T5 minus T4. Now one can appreciate that the efficiency of the cycle 2, 3, 4, 2 dash. That means this is smaller one. That is 3, 4, 2 dash and 2. These cycles. This efficiency of this cycle is less than the efficiency of the cycle 1, 2 dash, 5, 6. Now the combination of the two is the intercooled cycle, and hence efficiency of the intercooled cycle is less than that of the simple gas turbine cycle. Let us consider now the actual gas turbine cycle. The performance of the actual gas turbine cycle deteriorates from an ideal cycle for the following reasons. The first point is the compression and expansion processes are not isentropic. Thus, the efficiency of the compressor and the turbine must be considered here. Furthermore, the pressure losses will be encountered in ducts, combustion chamber, and heat exchanger. Next, the complete heat exchange in the regenerator is not possible. Furthermore, the mechanical efficiency due to bearing and auxiliary must be considered. So there will be some losses. Then the specific heat of the working fluid varies with the temperature. They are not constant. And mass flow rate throughout the cycle is not constant. So mass flow rate in the turbine would be more than that of the compressor because of fuel addition in the combustion chamber. So thereby the mass flow rate throughout the cycle is not constant. So these are the reasons why a actual cycle performance deteriorates with respect to an ideal cycle. And I'll discuss now one by one all the points. Now let us consider the compressor and turbine efficiency. Here I like to discuss about isentropic versus isothermal efficiency. So that means the questions I like to pose that in case of turbine or a compressor, should I consider the efficiency be isothermal or isentropic? The processes occurring in a gas turbine, being a high-speed machines, tends to be adiabatic. On the contrary, in a reciprocating compressor, being a slow-speed machines, the processes may be considered isothermal. Thus, the ideal compression or expansion occurring in the compressor or turbine respectively are assumed to be reversible and adiabatic. That is isentropic indeed for the gas turbine engine. So what I like to tell that for a gas turbine engine which is considered its efficiency as isentropic, while for a reciprocating compressor I may deal its efficiency as isothermal. Let us consider the isentropic efficiency of a compressor. And this TS diagram explains the process of compression, both actual compression and isentropic compression. And to explain that, I have indicated here the schematic of a compressor, where inlet condition is identified as 1 and exit as 2. That means P1 and T1 be the static pressure and temperature at inlet, along with the C1 is the speed of air, and that at exit would be equal to P2, T2 and C2. Now, I have identified P1 in TS diagram and the state point 1. And from state point 1, if I add C1 squared by twice Cp, I would land to 0, 1. C1 squared by twice Cp is the dynamic temperature. So 0, 1 state point has been marked, and thus P0, 1. Now from 0, 1, I have considered the actual compression process, which has been indicated by a dotted line, and 0, 2 is the exit point at 2. So I have considered P0, 2. Now from 0, 2, if you subtract C2 squared by twice Cp, you will get 2. So now you can add 1 and 2. So you can identify P2. So thereby P0, 2 and P2 are identified, and thus 0, 2 and 0, 2 dash. 0, 2 dash would be corresponding isentropic compression. So actual compression and isentropic compression has been identified now. So eta C can be expressed as the isentropic work absorption, by actual work absorption, that can be written as del 0 is, that is isentropic enthalpy change, divided by actual enthalpy change, that is del A0 AC. AC stands for actual. So del A0 can be written as Cp into T del T0. Thus, I can write eta C as T02 dash minus T01 divided by T02 minus T01. That is, it can be simplified as isentropic temperature rise by actual temperature rise. Now the isentropic efficiency for the turbine can be expressed as actual work production divided by isentropic work production. Note that for a turbine, isentropic work production will be higher than the actual work production. And the TS diagram here represents the expansion process. So I have identified both the total pressure and the static pressure and the corresponding the static point and the total pressure point. That means suppose 03 be the initial point, right, where gas is entering to the compressor, and P03 be the pressure at the entry. Now from there, if you subtract C3 squared by 2 Cp, you will get the state point 3. So we can identify P3. Now from 0 through 3 to 04, this farm line here represents the actual expansion process. So I can identify 04 point and thereby the pressure at exit 04. Now from 04, if I subtract C4 squared by twice Cp, I'll get the state point 4. So I can now identify P4. Now 03 to 04 dash, it's the isentropic work production, and 03 to 04 is the actual work production. Thus the efficiency for a turbine can be expressed as Cp into del H0 actual divided by del H0 isentropic. Now if Cp is considered constant, not a function of temperature, then it can be simplified as T03 minus T04 divided by T03 minus T04 dash. Now, so it will be actual temperature drop divided by isentropic temperature drop. Now, for compressor, I can write from the expression of isentropic efficiency. Now I can write T02 minus T01, that is actual temperature rise, is equal to 1 divided by eta C into T02 dash minus T01, that is isentropic temperature rise. So if we take T01 common, I can express T02 minus T01 as T01 divided by eta C within the bracket T02 dash divided by T01 minus 1. Now T02 dash by T01 can be expressed in terms of pressure ratio. Therefore, I'll get T02 minus T01, that is actual temperature rise in the compressor, is equal to T01 divided by eta C, T01 the initial temperature at the entry, eta C is the compressor efficiency, within the bracket P02 by P01, that is pressure ratio, to the power gamma minus 1 by gamma minus 1. Thus, this is a very important equation which tells us if you know the compressor efficiency, you can evaluate actual temperature rise with respect to pressure ratio. Similarly, for a turbine, I can express the actual temperature drop in terms of pressure ratio and the turbine efficiency. Thus, T03 minus T04 is equal to eta T into T03 within bracket 1 minus 1 over P03 by P04, which is pressure ratio, to the power gamma minus 1 by gamma. Furthermore, for an industrial gas turbine, which is a land-based unit, I can consider here P01 total pressure at inlet is equal to atmospheric pressure, and similarly T01 is equal to Tf, atmospheric temperature. However, for a aircraft, the situation is different, where a significant ram compressions occur because of intake and the forward speed has been diffused. Therefore, there will be pressure rise and thus the temperature rise. So here P01 is not equal to PA, and T01 would be TA plus CA squared divided by twice Cp, where Ca is the forward speed of the craft. Now I'll discuss on pressure losses. In an actual cycle, there will be pressure losses in the combustion chamber, heat exchanger, and in the ducts. Let us consider now del Pb is the loss in combustion chamber due to aerodynamic resistance, flame instability, heat adhesion. Similarly, del Pha be the pressure loss in the heat exchanger passage on the air side, where del Pag is the pressure loss in the gas side heat exchanger. Here, look, I have indicated on TS diagram a simple gas turbine cycle with pressure loss, where del Pb, del Pha, and del Pag are marked. And from this figure, one can appreciate that P03 rather will be lower than P02 because of this loss, and P04 will be higher than P01 because of loss. Thus, I can express P03 as equal to P02 minus del Pb minus del Pha, which can be expressed again as P03 is equal to P02 within the bracket 1 minus del Pb by P02 minus del Pha by P02. Often that combustion pressure loss and the pressure loss in the heat exchanger air side is expressed as a percentage of P02. So in reality here, one can appreciate that pressure loss at the entry of the turbine would be less than the exit of the compressor. Again, I am telling the pressure at the entry of the turbine will be less than the exit of compressor because of losses in the combustion chamber and heat exchanger. Similarly, P04 is equal to PA minus del PAG. Therefore, the P04, that is exhaust pressure from the turbine, will be higher than the atmospheric pressure because of loss. Furthermore, the pressure losses in the ducting due to aerodynamic resistance depends on the flow velocity and density of the fluid. It should be noted also that the pressure loss in the heat exchanger may reduce the power output of a gas turbine engine by as much as 10%. Thus, in an actual cycle, if heat exchanger is introduced, the output of the cycle will be decreased, although its efficiency increases. Now I'll discuss about heat exchanger effectiveness in brief. Please note that heat exchanger for gas turbine can be of many forms, such as the counterflow and crossflow recuperator, where the hot and cold streams exchange heat through a separate valve, or a regenerator, where the streams are brought cyclically into contact with a matrix which alternatively absorbs or rejects heat. I have indicated here a regenerative cycles where the heat exchanger is used. Thus, from the energy balance, one can write MC into Cp into T05 minus T02 is equal to MT into Cp into T04 minus T06, where MC is equal to mass flow through the compressor and corresponding mass flow through the turbine is represented as MT. Now, the effectiveness of a heat exchanger can be defined as the ratio of actual heat transfer to the maximum possible heat transfer. Thus, I can express the effectiveness as epsilon MC into Cp into T05 minus T02 divided by the maximum possible heat transfer, which would be equal to M2 into Cp T04 minus T02. Now, if I consider MC equal to MT and Cp is constant, then effectiveness can be expressed in terms of temperature ratio, which would be equal to T05 minus T02 divided by T04 minus T02. Furthermore, I'd like to state here that the effectiveness of a heat exchanger depends on its size, heat transfer area, and thus the cost. Furthermore, in an aircraft engine, because of the limitation of space, the use of heat exchanger is avoided. So this is one of the important points with respect to the aircraft engine, that in aircraft engine, because of limitation of space, the use of heat exchanger is avoided. I'll discuss now the mechanical loss. Now in all gas turbine units, the power required to drive the compressor is transmitted directly from the turbine without intermediate gearing. Thus, any loss that occurs is only due to the bearing friction and windage. Therefore, the mechanical losses is normally be very less, and it's about 1 to 0.5% of the input power. Now, the compressor unit input power per kg of air can be expressed as 1 divided by eta m being the mechanical efficiency, into Cp into T02 minus T01, where eta m, that's mechanical efficiency, is considered as about 99%. In some utility, if the gearing unit is installed between the turbine and the compressor, or between the turbine and the propeller, then the efficiency of the gearing unit must be considered. Regarding variation of specific heat, Cp, I'd like to say that for real gases over normal range of pressure and temperature, Cp is a function of temperature alone. And the same is true for gamma, because gamma can be related to Cp by the equation gamma minus 1 by gamma is equal to R tilde divided by m by Cp, where R tilde is the universal gas constant and m is the molecular weight. So here the figure 7 I have indicated the variation of Cp and gamma as a function of temperature for different fuel-air ratio. So what can be illustrated that Cp increases with temperature while gamma decreases with temperature. For preliminary calculations to be sufficiently accurate to assume the following and gamma for the compression and expansion processes, such as on air side we can consider Cp as 1.005 kilojoule per kg per K and gamma as 1.4. Thus the ratio of gamma minus 1 by gamma is equal to 3.5, while on combustor side, particularly after combustion, while calculating the turbine work output, CPG can be considered as 1.148 kilojoule per kg per K, and thus gamma G as 1.33, and thus the ratio of gamma minus 1 by gamma as 4.0. With respect to change in mass flow in turbine and compressor, we can say that mass flow rate through the turbine will be somewhat greater than that through the compressor due to addition of fuel. Furthermore, the effect of bleeding from the compressor for the purpose of turbine blade cooling must be considered here. Thank you for listening.